The Bayonet AUGV is a highly adaptable platform designed for surf zone exploration. It is made up of 3 individual sections attached by 4 pins and wet-mateable electrical connections. If these pins are removed, the components can be easily taken apart for transportation to and from the worksite. The highly modular construction of the Bayonet AUGV allows it to be quickly assembled onshore, deployed from a vessel, or even assembled underwater by a diver. The ignition key for the vehicle is actually a rubberized magnet that fits and compresses into the back right-hand side of the vehicle. That will actually give you the ability to allow power to go into the vehicle. So it's completely wet mateable and safe. So you can assemble this thing underwater, you can assemble it on the beach. It's very much designed to be dealt with in not the greatest of conditions. It's capable of handling multiple payloads. There's really unique integration of navigational sensors with a crawler such as this. So when we operate on land, you'll notice at the top of the pole or the mast in the back, there's a land-based GPS system. So that allows us to get a good navigational fix while we're operating, within the GPS satellite range. As soon as we go subsea, we're going to lose our GPS fix, and the software is designed to constantly monitor sensor inputs from our navigational system. So as soon as the GPS drops out, we automatically switch over to the inertial navigation system. And the inertial navigation system is a fiber optic gyroscope. It's an AHRS compass to give us heading. We also keep track of the track movement. So we have encoders built into the electric motors, which give us odometry across the seabed as well. And we can process all of that information to give us an extremely accurate navigation solution. We're typically operating at about between 0.2 to 0.3% distance traveled. So for a kilometer, track, we could potentially be off by about 2 meters start to finish on the end position. So as I mentioned before, there's multiple ways that you can communicate with the vehicle. You'll notice that there's a orange ball hanging off of the back of the vehicle. So inside of that buoy is actually an MPU-5 radio, and it allows us to have a very high bandwidth, long-range data connection. So in circumstances where the user is actively controlling the vehicle or actively monitoring the vehicle, you can have very, very high data transmits between the subsea vehicle and your land base station, or vice versa, a sea-based topside station. So this would probably be a good jumping off point to start getting the vehicle into the water and switching over to the UI. So what we'll do is Tom will go ahead and share his screen when we get the vehicle in the water, and then we can kind of go over how the user interface works and some of the navigational data points, the overall GPS and TIFF images. I'm just going to start to chat through a little bit of what we're seeing here so I can get everybody on the same page. If you'll notice in the top left quadrant of the screen, you basically have what I refer to as the Google Maps view. So the OpenSea software has the capability of taking TIFF files and actually superimposing them onto the screen. So you have more or less like a background image of where the vehicle is. It gives the end user a little bit more representative physically of where they are. So this is Plymouth Harbor back here. To the left is an old warehouse, and then to the right is more or less open water. There's some jetties and some other marina areas a little bit further to the right. So we're just approaching highish tide. So we've probably got about 3 to 4 meters of water, about 100 meters out. If we look over in the top right quadrant of the screen, that's the screen, that's sonar. So right now the sonar is in air. So you're just seeing what the sonar is in air. So you're Right below that is obviously the video feed. You'll notice in the top left portion of the screen, you'll see DPT parenthesis M, and then below that, like a bar chart. That's the depth that the vehicle is at in meters. So we can use that depth as we're recording a mission. The depth is also being recorded across the navigational points. So for every position that the vehicle has touched at a certain frequency, you're also recording how deep it was. What we do for beach profiling is we take a fixed length mast and we use the RTK, X, Y, and Z data. And then because it's a fixed length mast, we know that the bottom is, if it's a 2-meter mast, we know that whatever the RTK-Z measurement is 6 meters below that. So it can give you a very, very precise measurement with the RTK, or the depth sensor is, I think, plus or minus 30 to 50 millimeters. So it actually is a very precise depth sensor on the vehicle. That's a built-in standard function. If you kind of follow that depth screen down on the left-hand side, these are all of your secondary option screens. So the stop button is obviously exactly what it is. It's just a panic button to stop whatever you're doing. It'll stop the vehicle, stop the motors, and just leave it where it is. Right below that, we have a pause button. Moving down, we have checks and then measurement tools. So as you're doing different mission sets, you have different capabilities to measure different features, different distances traveled. Right now, you'll notice that there's a little white dot being placed behind the vehicle as it's going out into the water. So this is what we call the breadcrumb trail. Gives the operator a very good indication of where they have been traveling. And as you move through the water column, you'll see different items. The sonar will pick up different things. And if depending on your visibility of your video, obviously you'll get that video feedback as well. If we go to the bottom center portion of the screen, this is kind of the vehicle diagnostic screen. So in the very center, you have what a typical air pilot would see, your pitch and roll sensors. So the vehicle is set up so that you can actually limit the amount of pitch and roll that the vehicle will see. So in the event that you're going down really steep terrain or need to go up really steep terrain, you can prevent the vehicle from getting into a situation that you otherwise don't want to be in. Just to the left of that, you'll see port SOC and starboard SOC. That is the state of charge of the batteries. It's a visual indication of how much power you have left. As you drain the batteries down and you get further into your mission set, those will start to give you little warning indicators. If it's getting lower, it'll start to go yellow. If it's getting to a point where you need to return to home, it'll go to red. Right below that, we have our sensor feedback. So green, sensor is on, sensor is sending data. Grayed out, sensor is turned off. And yellow means that we have a kind of signal, but nothing that the navigation solution is going to use to process. So one of the beauties of this whole mapping and navigation sensor or software suite is that you have the ability to run actual mission plans. Let's just say you have an area of interest that you want to survey. You can literally draw a box on the screen, and you can choose between, I think, 4 different styles of lawnmower pattern. Obviously, the traditional up, over, down, over, up. There's a sawtooth pattern where you go up to a point, come down diagonally, up to a point, come down diagonally. There's a circular pattern, which allows the vehicle to more or less just do very broad circular motions to survey in a more circular, continuous motion. And then inside of each of those patterns, when you go to set that up in the mission plan, it'll ask you what kind of spacing you want to do. You could set your mission plan up for 100-meter spacing, or you could set it up for half-meter spacing. And then the software will go ahead and it'll just automatically populate that mission route. And, if it's a very narrow swath lawnmower pattern, you'll have a ton of waypoints. If it's a very wide area swath, then you'll just have a handful of waypoints. But the software does that in a handful of clicks on the screen. Here you can see Tom's going through and creating a new mission. So it's more or less a point and click type of operation. You can set in pre-known coordinates, or you can use the mouse if you're in an area that you don't really know what you're looking for, but you know kind of where you want to look. You can literally just either draw a square or put a number of mission markers on the screen and go ahead and execute that mission. So when you execute a mission, obviously you're trying to collect data and you're trying to report back on something. So we've made it fairly simple to go ahead when you start a mission to just hit a record button. So when you hit that record button, everything that the software system is seeing and capturing is then saved into a playback file that you can look at for future reference or for further analysis. That playback ability will allow you to see everything from the sonar and the video and the navigational points to everything within the actual system itself. So you can see how much current the motors have been drawing, how much sensor data you're collecting, and at different time frames. So it's a very, very valuable tool for post-processing a mission set. The software set operates across what we call safe C2. So it's safe communications. And the software is constantly assessing how strong of a data connection it has to whatever node it's working with. So if it's a high-powered radio or if it's an acoustic communications, the vehicle will actually determine what it can and cannot send in terms of mission plans or commands or communications both ways. So you'll notice on the screen that there's a number of different waypoints. These are just, self-clicked in waypoints. They weren't predefined, but if you wanted to put in predefined waypoints, that's fully doable as well. So the vehicle's actually traversing to its first waypoint here. As it goes along, it's going to reach its waypoint, and then it's going to redirect itself to its next waypoint. When it finally gets to its last waypoint, the vehicle will just sit and wait for its next command. One thing to note as you're going through and doing some kind of survey or exploration is that you can add in markers to different areas of interest. So if we were to approach a treasure chest and we see that on the sonar and the video, we would want to put a navigational waypoint on that location, and then you can type in free text as to whatever you want to say. So put in a waypoint and you could notate it and say, hey, this looks like a treasure chest. We want to either come back to this, or we just want to notate the navigational location so we can come back at a different time and see what it really is. So it's a very valuable tool for identifying and making notes as you're doing surveys and different explorations. We have what we call the OpenSea Edge box, which is it's two sets of high power CPUs. And we use those CPUs in conjunction with the forward-looking sonar to detect anomalies in front of us. And then the navigational algorithm will basically replot a path around that object. Now, as you're replotting this path around the object, if another object comes into sight, it will then take into account the other object and just start re-navigating itself around whatever objects are in front of us, and then try and return to the set waypoint that your mission plan has set up. So if we had obstacle avoidance on here today, you would notice the vehicle is trying to go in a straight line, but then it deviates from that straight line and is going around until ultimately it returns back to that mission plan. So small stones, small objects, the vehicle will just drive right over. The processing algorithm is set up to detect, I think, anything over 8 inches, so 200 something millimeters. So if the sonar picks up that smaller obstacle and we tell the system that, this size range is kind of our minimum that we want to deal with, the vehicle will traverse around it and then return to its mission plan point. The sensitivity of how big of an object you're looking for, there are, limitations with size and the capability of the forward-looking sonar. But we do also couple the obstacle avoidance with what we call ATR, automatic target recognition. And we have a database that we use to compare the sonar imagery to known targets. And by doing so, you can actually classify and identify objects of interest autonomously, and you can actually set the system up so that the vehicle will either pause and wait for a response from a topside command, or you can just have the vehicle note the location and the possible target of interest automatically. The OpenSea software suite is used across not just crawlers. It's used across many different ROVs, different hull cleaning robots. It's a very broad use software suite. It's very intuitive, and it's actually very easy to integrate. Different sensor packages. So it's a very nice piece of software. Yeah, so actually, we have multiple options on GPS. One of the services that we provide is beach surveying and the littoral beach profiling. So we use a RTK on a slightly taller mast, and we'll actually go out and do beach profiles for dredging companies and civil engineering companies that need to operate in the surf zone, higher current areas, typically places where a boat can't get to, and it's not exactly safe for a person to go out and wade in the water. We are on the beach right now doing surveys down in the southern part of the U.S. No, so actually, that orange ball that you saw hanging off the back of the vehicle is a towed buoy. So the crawler itself has a cable going up to the buoy. The buoy is floating on the surface, and we're connecting via MPU5 radio between the buoy and the shoreside laptop. So we have the ability to do two different recordings. So we can do a subsea recording, or we can do a topside recording, or we can do both. The available hard drive space is expandable, but when we're recording subsea in this type of mission, we're basically just capturing the navigational data, and then on the top side, we capture the full suite of data so that we don't have to have a big hard drive subsea. In an autonomous mission or something where you're communicating just via acoustic communications, we can have a larger hard drive subsea so that we are capturing this whole screen setup that you're seeing here. So the crawler runs at about 1.5 to 1.7 kilometers per hour. If you want to put a rear-facing camera on, that's no problem. So we can adapt multiple camera feeds. Um, we have a particular camera that we use on a regular basis. It's a Sidus small IP camera. It's a 300-meter depth rated camera, gives you a good image. We have typically found that in most operations, the sonar is really our eyes underwater. You'll notice that it's a very murky water quality right now. We've had a number of different storms that have blown through over the last week and a half and just stirred the water up to where it's very cloudy and the visibility is very poor. So you have the ability to adjust the fan range settings. So depending on how close or how far away you are to an object, sometimes you want to change your range fans. The range fan will communicate with the sonar, and as you go to a more broad or a higher meter range fan, you'll adjust your frequency out. And as you get in closer, it'll adjust it as well. You can also adjust the color temperature on the range fan. So I think in the bottom right corner of the UI, there's pinks and blues and reds that you can toggle between. So that is a good question. The current configuration of the sonar is a fixed mount orientation, but we can add in a subsea rotator to allow the beam angle to be moved, down or up in the water column if you wanted to use the sonar for inspection purposes. The configuration that we are using the vehicle in shown today is that the sonar is being used for navigational purposes. So we're using it to drive and avoid objects and to see what's in front of us. We're not necessarily doing an inspection of a wall or a dam or trying to look at the underside of a vessel. But it's a integration of a rotator off the shelf and then mounting that to the vehicle. So we've worked quite a bit with Reach Robotics. We have all the configurations and control interfaces to utilize a Bravo or Alpha manipulator. The crawler is actually an amazing platform to put a manipulator arm on because you have a very stable platform and a very rigid base that you can do very fine articulation with the manipulator depending on which one you prefer. The vehicle as we're showing it does not have a manipulator arm built into it. It is a pretty simple integration to get the manipulator arm mounted onto the vehicle. The vehicle itself is designed to very easily adapt different sensors and different auxiliary equipment onto it. We have a fixed bolt pattern on the top deck plate that allows us to very quickly adapt and make mechanical mounts for different devices. We also have a very close integration with a company that makes active magnetometer arrays. And we have proven very successful in doing UXO surveys and subsea missile detection using this towed array. And it allows us to take the sensor input, and as the magnetometer finds anomalies, report back to the user, hey, at this position, we have a very large anomaly magnetically. that we should look at for the future. The Apex system will detect up to, I think, about 1.5 to 2 meters under the sand. Now, there's some caveats with that. The size of the object is going to dictate the maximum depth of burial. So if it's a large metallic object, the Apex system would pick it up if it's much deeper. If it's a small, 25 millimeter metal object, you're looking at about probably maybe 200 to 300 millimeters subsea. So it's the maximum depth condition is largely based around the size of the object. So the buoy tether is actually a Kevlar braided strength terminated cable. We do not recommend that you pick it up by the buoy cable, but you probably could. We actually have pre-defined lift points for the vehicle. So in the event that you needed to recover it off the seafloor, we have predefined lift points, and you can pick it right up. What we like to do is actually have a surface recovery buoy. So just a small float attached to a lift line, and the vehicle just pulls that around as it's doing its surveys. And if there is an issue or some kind of catastrophic event, you can just recover the buoy and either attach it to an A-frame or a lift bag, a davit. There's a lot of different options that you can go there. So it can be launched from a boat in a number of different ways. You could lower it to the bottom if you have a boat with a hoist or a lift. We have very successfully driven the vehicle off the bow of the boat and just let it sink to the bottom. It's very much like a cat. It seems to always land on its feet. Granted, if it's a very high turbulent, high current condition, then it's a question mark. It would probably be better to lower it. But we have very successfully just driven it right off the bow of the boat and had it land on its feet. The vehicle has about 220 kilos of tow force. If you translate that into payload, you can put anywhere between 200 to 300 kilos on top of the vehicle. It's a very, very rigid structure. So the limitation is the ability of the tracks to actually propel that payload through the, across the beach or into the water. But we do have to take considerations into how high up that payload is and where center of mass is and things like that will ultimately wind up. So the 350 is about a 2 meter length and 1.7 meter wide. We typically use the 350 in higher surf state conditions. So we had discussed, the use of RTK in doing shoreline surveys. We operated a 350 in 2 to 3 meter weather conditions with a 4 meter tall mast, basically a sailing mast with a RTK mounted to the top of it to do very high accuracy beach profiling. The 250 is an extremely stable platform as well. in higher surf conditions, we just need the wider and longer base stance so that it has less susceptibility to tipping. Yeah, so this vehicle has a KBH 1750 3-axis fog mounted in the port side track assembly. We use a Spartan AHARS compass. The depth sensor is a Keller, and the track odometry is an encoder built into the drive motors of the track assemblies. Yes, you could put it. You can post process into like a Delphi or any other post processing software. We capture all the raw sensor data in the recorded mission. So the vehicle is currently depth rated to 100 meters. The main limiting depth rating is actually the battery assemblies. So we use a 1 atmosphere enclosure on the batteries. It's a rectangular structure, but we have basically stuck at the 100-meter depth rating. Sea state, we have sent this out in sea state 3. It's sea state. The sea state nomenclature is tough to assess on the shoreline, so I typically will describe it in terms of wave height. We have steadily used this actual vehicle in 2 to 2.5 meter wave breaks, going out, coming back in, operating out mid-water, hours and hours and hours on end. Yes. So we actually were doing testing yesterday with our Ocean Comms acoustic modem, and we have a full range of different ACOMS modems that we've used. They're bolted onto the vehicle and plugged in, and away we go. It's very dependent on the modem that you use, but with the Ocean Comms modem that we've kind of grown fond of, anywhere between 500 to 600 meters with still good data transmit capabilities. The water depth and the overall range plays a big factor in that. The shallower the water, the less range you're going to get. The deeper the water, the better range you're going to get. The general rule of thumb is if it is a serial or Ethernet device, then we essentially can communicate with it and process the information and data. There's a lot of different ways to recover, and there's a lot of different ways to manage the umbilical. It really will boil down to the operational scenario. We have methods for doing a lot of these different things that you're asking about. So, one big area that we find ourselves working with quite a bit is, enclosed areas, tunnel type inspections. So we can adapt a fiber optic tether so that you can actually have a live communication to the vehicle with very high data rates over, a significant distance. One single mode fiber can travel anywhere between 9 and 10 kilometers. From a buoy lifting device perspective, if we use a higher breaking strength Kevlar cable, we can pick the vehicle up by the umbilical without hesitation. This is a lighter weight cable that we use for demos and beachside operations. It's easy to manage, and it's not a terribly expensive cable. So it really falls down into what it is you're trying to do, and we can certainly manage the solution for your overall operation. So as we drive along the beach, it's very dependent on, and we have a GPS fix. The software will use that as your navigational true position. As you go underwater and get subsea, anywhere between software will actually switch over to the inertial navigation system, good data transmit capabilities, sensory feedbacks for navigational accuracy. So we're constantly, because we are an amphibious vehicle, we're constantly jumping between GPS fixes and inertial navigation solutions. But that's how we handle our navigation, and we do a lot of testing to prove out that the subsea navigation is as accurate as we need it and want it to be.